moving into 6.2, we've seen how we can relate these angles in the unit circle. Let's even just take a segment of it for now. That if I had some angle theta, I could relate that to the length along the path along the unit circle and get its radian measure. But what I can also notice is that if I drop a perpendicular down, that angle theta exists in a triangle. So if I look at just the triangle on its own, I've got three sides related to that right triangle. I've got the opposite, I've got the adjacent, and then the hypotenuse. And if I remember from chapter 5, that point there on the unit circle where they meet has coordinates cosine of theta, sine of theta. Those were the trigonometric functions that I was able to relate to that angle theta. But if I'm on the unit circle, that hypotenuse is length 1, and the cosine being the x-coordinate is that distance there, and the sine being the y-coordinate is that distance there. And we get a nice relationship then between these trig functions and how they were related to the unit circle, and how I can relate the exact same things to a triangle built out of that same basic angle theta. So here's my triangle, here's my angle theta, and I'll abbreviate these as hypotenuse, adjacent, and opposite. And for any angle theta, we get these nice relationships. Sine of theta is opposite over hypotenuse. Cosine of theta equals adjacent over hypotenuse. Tangent of theta is equal to opposite over adjacent. Or the way that I always learn to remember these things, so toa. The sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. The tangent is the opposite over the adjacent. And we can use our knowledge of trig functions from sections 5 to get that the cosecant of theta is hypotenuse over opposite. The secant of theta is hypotenuse over adjacent. And the cotangent of theta is adjacent over opposite. So let's do a quick calculation. Suppose I had this triangle, right triangle with sides 5, 12, 13. Nice perpendicular lines there. And you can check, using the Pythagorean theorem, that this is indeed a right triangle. So if I had some angle theta, sine theta, opposite over hypotenuse, 5 over 13, cosine theta, 12 over 13, and tangent of theta, 5 over 12. All without having to even know what theta is. I don't even know the angle measure, the radian measure of theta. But I know enough, just from knowing the side lengths of the triangles, that I can compute these values. Secant, cosecant, and cotangent are computed similarly. A problem you might be asked to do in the homework or in the book to solve a triangle. So suppose I gave you this triangle. I'm going to put an angle of pi over 6 down there, angle of pi over 2 over there since it's a right triangle, and then let's say that side is length 12, and those are just A and B. I don't know what they are. So if we say we want to solve a triangle, we want to determine as much information about the triangle as we can, which means I would like to find out what the length is of this side, what the length is of this side, and what the measure is of this angle. So let's figure out the sides. I know that sine of pi over 6, based on what we said before, is going to be the opposite over the hypotenuse. It's a over 12. But we also know from what we did in chapter 5 that sine of pi over 6 is equal to a half. We sorted that out from the chart we made back in chapter 5. So 1/2 is a over 12. So a is equal to 6. Similarly, we can use the cosine to find b. We have the cosine of pi over 6 is b over 12, but cosine pi over 6, we know from our last chapter, square root of 3 over 2. That's equal to b over 12. So b equals 12 square root 3 over 2, or reducing that to 6 square root 3. So b is equal to 6 square root 3. The last thing we need to do is sort out this angle over here, but that's pretty easy to do. If you remember, the angles in a triangle add up to 180 degrees, which we know is also equal to pi. That's the radian measure that's equal to 180 degrees. So from here, we have, let's call this one theta, that's our unknown. We have theta plus pi over 6 from this one down here. This is a 90-degree angle, or measured in radians, pi over 2. And that has to all add up to pi. So theta is the last piece, and we get 2 pi over 6, which is just pi over 3. The triangle solved. We found the length of all three sides, and we know the measure of all three angles. You can also use this to sort out some different applications. Suppose we'll go with, let's see, we'll even get some colors here. There's my ground. There's my sunshine. The sun is always smiling. And if the sun is shining on, let's say, a tree, and then we've got a shadow on the tree. Now, if the shadow is 532 feet long, and I know the angle that it makes with the sun, I should be able to find out, using some trigonometry, what the height of the tree is. Because I've got a nice right triangle there. So I've got some height h, I've got 532 feet here along the base. What I need to know is this angle. And that angle might not work out very nicely. You might only have the measure in degrees, it might not be in radians, it might be something where we need to approximate, which is where the calculator comes in. So suppose I had 25.7 degrees. Well, I'm going to need to be able to sort this out, and for a right triangle, I've got, for this given angle, I've got the opposite and the adjacent. I don't know the hypotenuse. So, back to our SOHCAHTOA, what do we have that relates the opposite with the adjacent? The tangent. So I'm going to get that the tangent of 25.7 degrees equals the height divided by 532. So the height, go to 532 times the tangent of 25.7. Like I said, you'll need a calculator in degree mode to compute this. It doesn't have a nice angle, a nice measure that we can use from our chart. But if you go through and calculate this, you'll get about 256 feet. So these trigonometric functions are important. Right triangles show up all the time in mathematical models. And as you need to find out more information about those triangles, figuring out distances, figuring out relationships between different objects that are moving through time and space, trigonometry is your friend. It can be used to look at things that are measuring, like I said, either modeled by a triangle, both triangular models and the stuff with circular motion. It's all going to come back to trigonometric functions.